Hi all, and welcome to the Emergent Vision Technologies high-speed imaging presentation. I am John Eilert, President, CTO, and company founder, and I look to present our perspective on high-speed imaging. Some highlights about Emergent are presented here. We are a multi-award winning company with a focus on high-speed GigE Vision product. We have many years shipping product at speeds of 10 GigE, 25 GigE, and even 100 GigE. We have a strong focus on providing end-to-end technologies and comprehensive support for our customers' applications. Lastly, products presented are available now. Here is a quick snapshot of the adoption of GigE Vision products ranging in speeds from 10 GigE up to 100 GigE. Emergent has shown how top performance can be achieved and opened up many markets, including machine vision and entertainment, to the use of such technologies. Some companies are just now leveraging our efforts towards releasing 25 gig and higher speed product, but still a ways to go to provide ratified, mature, and performance product. The focus of this presentation is going to be on the technologies involved in high-speed applications. These include interfaces and their protocols, processing technologies, software, and finally the cameras. We will take a moment to understand the technology behind GigE Vision. GVSP is the Ethernet streaming protocol used in the current standard. A stream is made up of multiple frames or images. Each frame is made up of a leader packet, multiple image or payload packets, and a trailer packet. All packets follow the UDP Ethernet protocol, which is an unconnected protocol. This simply means that the camera sends the packets and leaves the receiver to do its job of placing data in the destination buffer. Being an unconnected protocol, this means it has zero network overhead, which leads to maximum network performance. It also means fundamentals like multicasting are supported. We must properly design our receiver to avoid data loss. CXP also follows the same protocol and leaves the receiver to its job of placing the data in the destination buffer. This leads to top performance and lowest latency and jitter with a quality receiver. I will note that the inability of some companies to design a quality receiver has led them down alternate paths. Conventional GVSP uses header splitting in software to strip the headers off the GVSP packets and place the image data from the payload packets into a contiguous memory buffer. This process raises CPU usage, but more importantly eats up 3 times your system memory bandwidth usage over a zero-copy implementation. This results in a 33% efficiency for the system, which factors into the system cost in a number of ways. This is an example of a poorly designed receiver, and many in the market are still doing this even at 10 GigE, but we still see cases where some companies have trouble running multiple 1 GigE cameras on a single server, all related to poor receiver design. This short animation illustrates the process of splitting GigE Vision network packets into images. Headers, leaders, and trailers get consumed by a control process, while the image portions end up in a contiguous memory buffer. When software is used for this process, the whole packet is written to memory, and then the image portions need to be read out of the memory and written back into another memory location in a non-fragmented or contiguous manner. This process can be done in software, which costs 3 times the memory bandwidth, or it can be done by the card's header splitting features for optimal performance. This short animation illustrates the triple memory bandwidth usage of a system that does not utilize zero copy or header splitting technology. A system like this can result in data loss as memory bandwidth is exhausted. Data loss occurs when the buffer in the network card overflows, when the CPU and memory do not permit further transfers. This, incidentally, is what RDMA proponents compare with when discussing pros and cons of traditional GigE Vision and RDMA, which is very misleading as this is the worst case example. TCP is one protocol explored by some to improve the performance of GigE Vision. Some even claim this is a guaranteed transfer mechanism, which is completely false. TCP is not a zero-copy process, so it triples the required memory bandwidth. In addition, TCP is point-to-point, which converges this protocol with CXP and USB, which all but eliminates the benefits over those protocols, especially since CXP is adopting the Ethernet physical layer in newer revisions to address its own deficiencies. In all senses, TCP is a non-starter for performance applications and amounts to little more than marketing noise. This short animation illustrates the triple memory bandwidth usage of a TCP-based system that does not utilize a zero-copy technology. A system like this can also result in data loss as memory bandwidth is exhausted. The difference compared to UDP is that for TCP, the camera maintains a buffer and a resend mechanism in the camera to deal with system backups. The problem is that this buffer will also overflow, which again leads to data loss. Despite its deficiencies, CXP has a zero-copy solution, an appropriately sized buffer in the frame grabber card to deal with system backups. With zero copy, we minimize the memory bandwidth since only one write is performed to memory. Additionally, with a properly configured server, this also leads to minimal backups and a steady flow of data from camera to system, which minimizes latency and jitter. This short animation illustrates the zero-copy memory bandwidth usage of a CXP-based system. We see in the first part of this animation the system is not optimized, and thus even the appropriately sized buffer in the frame grabber card overflows. In the second part of the animation, data flows freely and reliably thanks to zero copy and system optimization. RDMA RoCE is another protocol explored by some for the same reasons as TCP. Some will continue to claim that this is now the guaranteed transfer mechanism, which is again false. RDMA is a zero-copy process, which is its primary benefit. As with CXP, with zero copy, we minimize the memory bandwidth. Additionally, with a properly configured server, this also leads to minimal backups and a steady flow of data from camera to system, which minimizes latency and jitter as long as buffers are not exercised. Also, as with CXP, even with zero-copy technology, a system that is not optimized will lose data as buffers overflow. Performance is never guaranteed unless a system is well designed and margined. An important note is that TCP cannot support a fundamental networking technology like multicasting, and RDMA in its intended connected use will not either. RDMA is providing a non-connected mode, which would bring us back to the current GVSP standard, with which a zero-copy receiver would achieve the same or better performance. It is important to remember that RDMA and TCP were designed for large, discrete data block transfers on the internet, with many multiple hops through switches and routers with dropped and out-of-order packets. In machine vision, the systems are closed with controlled routing if switches are used. Packets never come out of order, and resends or flow control are not needed. A strong reminder also that TCP and RDMA are proposals to the GigE Vision standard and far from ratified. RDMA RoCE v2 was ratified in 2014, and GigE Vision only started discussing this option in 2020. It is expected that if RDMA support for GigE Vision is ratified, that this will be a couple of years out. Rest assured, as the high-speed Ethernet leader, that Emergent will integrate the RDMA addition if and when support is ratified. This would be a small effort and would be backward compatible with all existing product we sell and support. This short animation illustrates the zero-copy memory bandwidth usage of an RDMA-based system. We see in the first part of the animation the system is not optimized, and thus even the appropriately sized buffer in the network card overflows. The difference compared to CXP is that for RDMA, the camera maintains a buffer and a resend mechanism to deal with system backups. The problem is that this buffer can also overflow, which again leads to data loss. In the second part of the animation, data flows freely and reliably thanks to zero copy and system optimization. Zero copy with header splitting is indeed possible with modern NICs by NVIDIA, Mellanox, Broadcom, Intel, and Marvell. Emergent has implementations deployed with NVIDIA, Mellanox, and Broadcom, which are the primary NICs explored by those experimenting with RDMA RoCE, which eliminates any concerns surrounding interoperability. In fact, Emergent has been using this same method for over 15 years and have the maximum design-in densities of any interface standard with reliability to match. The same approach is also used for SMPTE 2110 for the massive media and entertainment market. Zero copy does not guarantee zero data loss in any interface or protocol implementation. Any performance system still needs proper design and margining to achieve desired results. This goes for CXP, RDMA and RoCE, and even optimized GVSP implementations. But we can guarantee that the optimal GVSP implementation will equal or better RDMA RoCE without turning GigE Vision into a point-to-point protocol and eliminating what has made GigE Vision the most flexible and popular interface over the years. It is important to remind that when the retransmission feature of RDMA is engaged, that this is a sign of backup in the system, which is also a sign of undesired latency and jitter. It is also important to remind that CXP doesn't use resends and flow control, yet is able to sustain high data transfer rates with optimal receiver performance, low latency, and jitter. Much of this can be attributed to zero copy technology and adequate buffering on the frame grabbers required for CXP. Low-cost NICs often lack sufficient buffering capability. However, modern NICs are readily available at cost-effective price points with ample physical buffering. It is worth noting at 25 gigabit per second and higher that the familiar PoE or Power over Ethernet is dead. Thus, new deployments should be focused on SFP technologies and distributed power systems. It is also noteworthy, even at 10 GigE speeds, that the big NIC providers do not support PoE, which forces camera vendors to sell their proprietary card solutions. This short animation illustrates the zero copy memory bandwidth usage of an optimized GVSP-based system using zero copy. We see in the first part of this animation, the system is not optimized, and thus even the appropriately sized buffer in the network card overflows. In the second part of the animation, data flows freely and reliably thanks to zero copy and system optimization. This slide is an illustration of how the proposed or ratified changes are converging the interface standards. USB remains mostly the same, but is a point-to-point technology. CXP has adopted the Ethernet physical layer, converging towards GigE Vision. GigE Vision plus RDMA and GigE Vision plus TCP, if and when ratified, is converging to CXP and USB as a point-to-point technology. This is perhaps 2 years out. GigE Vision plus GVSP will maintain its integrity and feature set and not converge with the other protocols. This slide highlights the point about multicast technologies. GigE Vision plus GVSP is currently the only protocol which supports this fundamental networking feature. Other standards will be quickly dismissed in applications requiring efficient redundancy and distributed processing. This short animation illustrates how the data from one camera can be sent to multiple devices for parallel processing. A simple use case could even be where a separate system is used for display, while one system performs intense calculations. Zero copy minimizes the CPU and memory bandwidth utilization by writing to memory only once, but we can avoid that transfer altogether by writing directly to the GPU. This is called GPU Direct, and it makes sense in many performance applications to send data directly to the GPU for processing and then taking the lower bandwidth results to the CPU and memory for user or system interaction. Emergent has been supporting GPU Direct with NVIDIA GPUs on Windows and Linux for over 4 years in a variety of applications. NVIDIA RTX A6000, 5000, 4000, Orin, Xavier are used in many applications using Emergent cameras. Unfortunately for RDMA users, NVIDIA and Mellanox only allow GPU Direct on Windows to select partners such as Emergent, and this OS is where 80% of machine vision applications continue to be deployed. Linux, however, does remain an open option for RDMA with GPU Direct for all. This short animation illustrates the zero transfer process using GPU Direct, which completely bypasses the memory and utilizes only the PCIe endpoints of the CPU for zero memory utilization and zero CPU utilization. Zero copy is great. GPU Direct improves on this a lot, but it would be the ultimate achievement if we received and processed the data from the cameras all on one card. In this case, CPU, memory, and all server resources are not used at all. Emergent is supporting AMD Xilinx Alveo cards for this very purpose and have multiple performance applications leveraging this technology. Emergent is also working closely with NVIDIA to bring BlueField NIC support. Think of BlueField as the merging of NVIDIA NICs with NVIDIA GPUs. In both cases, the computer can be a very low-end PC, which primarily supplies power to the chosen card. This short animation illustrates the FPGA card process, which completely bypasses the memory and CPU for 0% memory and 0% CPU utilization. This is a real-world example system based on which many of our customers are deploying systems. Emergent is currently providing turnkey systems just like this as well. The largest system of this type uses 40 HB25000 SB 25 megapixel 25 gigabit per second cameras running at 90 frames per second and have in fact scaled the system to 240 cameras. Switches are used to multiplex the cameras to fewer NIC ports in the server and also to provide 1 microsecond accuracy synchronization using PTP. This short animation illustrates the flow of data in such a recording system. As with all of Emergent design systems, this results in zero data loss due to zero copy and proper system design. This is another real-world example which uses the same camera setup of example 1 but uses GPU Direct to send the camera data directly to GPUs, which performs H.265 compression, and the compressed images are stored locally on disk, as well as streaming using RTMP to clients like YouTube. At 30 frames per second, we are running this system with as many as 48 cameras, using a 48-port switch, while still running on a single mid-range server and CPU. This short animation illustrates the flow of data in such a recording and streaming system. Our last real-world example has two of our fastest 100 GigE cameras running at 10 megapixel and 1000 frames per second, being sent directly into a Xilinx U55C Alveo FPGA card, where the customers are performing their own custom processing. Actually, these same cameras are used in other recording or GPU Direct applications, but for the absolute highest performance, custom processing, some turn occasionally to FPGA cards. This short animation illustrates the flow of data in such an FPGA processing system. We introduce now the Emergent high-speed camera ecosystem, where all items we provide or recommend are thoroughly tested at both the component and system level. Let's first have a look at the cameras we provide at Emergent. Emergent area scan cameras are best known for covering an extremely wide range of resolutions and frame rates. We incorporate all the best sensors from Sony and G-Pixel. Sony boasts very high image quality with resolutions and frame rates a perfect match for the Emergent 25 GigE Bolt series and 10 GigE HR series. G-Pixel boasts high image quality, with resolutions and frame rates that push Emergent 100 GigE Zenith series to its limit. Emergent line scan cameras are best known for covering an extremely wide range of resolutions and line rates. We incorporate all the best sensors from GPixel. GPixel boasts high image quality with resolutions and line rates that push Emergent 100 GigE Pinnacle series to its limit. Emergent 25 GigE XL and 10 GigE Pace models nicely round out the line scan product portfolio. This animation illustrates a typical task of an area scan camera, which is inspecting objects on a production line. The cameras here are hardware triggered by the sensor looking for objects on the conveyor. Images are transmitted with low latency and jitter back to the computer for analysis and action. Generally, the object under inspection is captured fully in a single image. Emergent area scan cameras have 3 inputs and 3 outputs with opto-isolated and TTL options, depending on your application needs. This animation illustrates the same task with a line scan camera. Generally, line scan cameras are used for scanning a continuous web of material like print or fabric, but does not preclude applications as shown here with discrete objects. The camera images here are hardware triggered by the sensor looking for objects on the conveyor. The individual lines of a given frame are triggered synchronously through the use of the continuous encoder signal shown in green. The lines of a given image are immediately transmitted back to the computer and assembled in the user buffer with zero-copy technology. Emergent line scan cameras have encoder RS422AB inputs, 1 trigger input, and 2 outputs. TDI line scan cameras are used to expose the same line on the object multiple times to allow either higher speeds with the same lighting or the same speed with lower lighting brightness requirements. TDI achieves this by having multiple lines in the sensor, with each line exposing multiple times, and the exposure or line rate is perfectly synchronized to the movement of the conveyor through the use of the encoder. With such a broad range of products, we find it helpful to chart out the various resolutions and frame rates provided. At 10 GigE, the products range from 0.5 megapixel at 1500 frames per second up to 50 megapixel at 23 frames per second. At 25 GigE, the products range from 0.5 megapixel at 1600 frames per second up to 127 megapixel at 17 frames per second. And at 100 GigE, the products range from 2 megapixel at 3462 frames per second up to 152 megapixel at 16 frames per second. And finally, for line scan, the products range from 4K at 172 kHz up to 16K at 400 kHz, with a special nod to 9K TDI at 600 kHz. Well, that's a lot of high-speed cameras. So, to find the right camera, you can visit the online camera selector from the Emergent website. Enter in your application critical parameters to filter down to suitable models and review other more detailed specs by showing other columns. Finally, click the link to go to the camera product and research page. Works on PC or cell phone and significantly shortens the time required to find the right camera for your application. For those who have worked with Emergent, they know we are experts in areas of server technology and turnkey supply, from low-end PCs to high-end dual CPU technologies. We work with you to ensure you have all you need for the most productive development and deployment, and we're always there to lend a hand when you have difficulties, with extremely quick turnarounds on even the most challenging problems. We are experts in U.2 and M.2 storage solutions, and the associated host cards for these storage devices. We also have tested and fully integrated solutions for NVIDIA GPU-based product to allow quick prototyping with any Emergent camera. And most importantly, we support GPU Direct on both Windows and Linux. We also have solutions for those wanting to develop and integrate custom FPGA image processing for their most demanding applications. We support the major NIC brands like Mellanox and Broadcom with GPU Direct support and through our performance drivers, we easily provide the best-in-class performance with zero data loss. Emergent provides its own FPGA-based cards for more specialized applications. We are experts in switch technology and have solid relationships with the major switch manufacturers. We can give you ground-up support in switch programming and integration to take this right through to deployment as we do with our turnkey customers. We have Emergent certified cabling and transceivers to ensure the product you use will perform appropriately. Canon EF support is available for auto iris and focus applications. Standard mounts are supported, and custom adapters are an option as well. Lastly, the glue that holds it all together. Our award-winning eCapture Pro and eSDK are the most flexible and comprehensive softwares available from any camera manufacturer. Here we answer the question about what we do with all of this high-speed data that the cameras output. Our eSDK is the low-level software programmer option for complete custom application flexibility. It has runnable source code examples which exercise all of the critical functionalities like efficiently grabbing frames, PTP synchronization, GPU direct, multicast, I/O triggering, and more. Our eCapture Pro software is more application-based with a focus on system deployment, rapid prototyping, and includes options for customized GPU and FPGA card processing. We handle all the heavy lifting associated with bringing images to your processing resource and do so with top performance. You focus on your application code. Let's watch eCapture Pro in action in the following video. Seeing is believing. Let's add a local server to the eCapture Pro system graph. All discovered devices are shown. We add 2 network interfaces, we add all the cameras on those interfaces coming from the switch, and lastly we add the M.2 and GPU to the graph. We now configure the cameras with the desired settings. 24, 25 GigE cameras at 4K and 30 frames per second. With this complete, we start camera streaming. For this demo, we have one camera with a lens on and the others with a lens cap on. Let's fine-tune the camera with the lens on. In the data flow graph next, we connect our H.265 encoding instance to the M.2 drive to instruct all encoded video to be stored there. We then connect all the cameras to the input of this encoding instance. And lastly, we restart the cameras and tell the system to run this particular task. Next, we create an RTMP endpoint and a second H.265 encoding instance, which we set to run at a lower bitrate and resolution suitable for an RTMP client like YouTube. We send the stream of one of the cameras to this instance. We then run the system once again, and while the system is running, we jump to our YouTube channel and watch the RTMP streamed video. Now we take one of the saved H.265 files, decode and convert it to MP4, and then let's play this video. Now let's run 24 times 25 GigE cameras at 4K and 60 frames per second. We will add another GPU to the system and complete the configuration steps as in the previous section. Lastly, let's run 48 25 GigE cameras at 4K and 30 frames per second. We need to add another dual-port 100 gig NIC to the system, and then reconfigure to have each GPU handle 24 cameras at 30 frames per second. Then we run the system. We will also note all the green items in the status bar, which report potential problems, such as dropped frames, missed saves, lost PTP sync, and more. They're all green, indicating no errors found. This is an astonishing task for a system comprised of only a single mid-range server, 2 dual-port 100 gig NICs, 1 48-port switch, and 48 25 GigE Emergent Bolt Series cameras. I will emphasize that this performance is already being leveraged for a wide variety of applications, from machine vision to volumetric capture and everything in between. No other camera manufacturer even comes close to this performance, and are too busy just making sure their 2 camera systems do not lose data. And for third-party softwares that have high-performance GigE Vision drivers, or those that utilize GenTL for access to our top-performance drivers, one can use Emergent cameras quite effectively in these environments. Enter the high-speed world of imaging by leveraging Emergent as a partner, and take advantage of the ecosystem we have developed and continue to develop, so you can hit the ground running in your application. I wanted to provide a couple of examples where customers have come to us reporting a poor experience with another vendor's high-speed camera product. In one such recent example, we have 5 GigE cameras on a single PC. Over a 2-year period, the vendor made many attempts to resolve drop frame issues, but never could. In another example, the customer was trying to run 8 10 GigE cameras on a single PC. The vendor's comments were that they'd never tested more than 2 cameras per PC. Both of these customers are now happily using Emergent product. There are 2 very disturbing problems here. One is the poor performance some vendors are offering for their high-speed camera product, and the other is that a vendor would actually sell multiples of 8 cameras without having a discussion about what the customer's goals are to ensure the product can meet their needs. The critical lesson here is make no assumptions about any company's ability to provide a quality high-speed implementation for any camera count. Experience, dedication, and a solid track record in high speed matters. Our cameras are everywhere you care to look. We dominate in certain spaces where adoption rate is more rapid. We believe other spaces will follow, especially where factors such as performance, cost sensitivity, system simplicity, and time to market are at play. As you can see, Emergent has the highest performance camera portfolio, and we keep our overall product portfolio focused. We innovate, develop, adapt, and expand the markets we enter, and have the foresight to do so. Please do contact us for further details, and we appreciate you taking the time to view our presentation.